All right, so let's talk about hydrostatic pressure and force. So you've probably experienced, even if you haven't done any, deep sea diving, but you may have done some snorkeling, or you may have, maybe you have dived to the bottom of the deep end of a swimming pool, and you recognize that, you feel that pressure of the water surrounding you. And so that's what we're going to talk about. The pressure depends on the depth that you're at, right? And it depends on the volume of water above you. So at any given depth, and here they're using H to indicate depth. So using a variable h for depth, which I don't really like because I think of h as being height, which you measure from the bottom up. Depth we're measuring from the top down. So I don't know that I care for this h, but that's what your book uses here. So at any given depth h, right, the pressure is essentially the volume of the water. Of 1 square meter of water has a volume of 1 by 1 by h, right? And then the density of water is 1,000 kilograms per cubic meter. And then if we take that times the acceleration of gravity, we end up with this 9,800 times h Newton meters. And again, this is weird notation here. Newton should be Newton, it's Newton per meter squared, okay? I usually use a capital N for Newton, and I don't know why the book uses NT, because I don't think any never seen NT. I always think it's capital N. All right. So anyway, so we have an equation here for pressure at any given depth. All right. So 9,800 times the depth gives you the pressure at that depth. Now that's in the metric units, right? That's in your SI units. If we're working in the imperial units, then we're talking about the pressure is in pounds per square feet, so we can take 1 square foot times the depth, which gives us the volume of water above you, and then we can multiply by the density of water, which is 62.4 pounds per cubic foot. Okay, so the pressure is 62.4 times h pounds per square foot at a given depth h. All right, so in general, this is just a table that shows you kind of the units we're going to be using. It might be something that you want to refer back to. The density gives you the density of water in either the SI units or imperial units. So one important principle of fluids is that the pressure is the same in all directions at any given depth. So, it's the pressure pushing down, but it's also the pressure pushing to the sides. If you dive down, you don't just feel the pressure on your back, you feel in your ears and in all directions. So, so this is again just reiterating the pressure at a given depth. And we're using, again, h, because that's what your book uses for the depth, is just either 9,800 times h in newtons per meter squared, or 62.4 times h in pounds per square foot. And then we can find the force by taking the pressure times the area. Okay, so this is going to help us look at hydrostatic figure out the force due to water. And if the force, let's see, if we were trying to find a force on a surface in which the depth varies, right? So we have, say, some sort of vertical surface, like, say, a dam or the ends of a trough or something like that. Then we can divide the surface into horizontal strips, and each one of those horizontal strips will be approximately at a constant depth. And then essentially we'll use an integral to add up the forces on each of those strips, and that'll give us a total force. So let's look at this example. So we've got a dam, okay, and the dam has a trapezoidal shape. The top is 50 meters wide. the bottom is 30 meters wide, and the height is 20 meters. So if I just kind of, I'm going to sketch this over here. So this is kind of what it looks like. The dam looks like this. So this would be the bottom of the dam, and we have the top of the dam. It's 20 meters high. The top is 50 meters, and the bottom is 30 meters. Okay, I'm just going to sketch it kind of small there because I want to reorient this in order to evaluate the force. So what we need to do is, break this up into strips, right, that are at a constant depth, and then figure out the force on one of those strips and then just add them up to get the total force. The problem I have, though, with this is that we're measuring depth from the top down. So what happens is, at least for me, I get all messed up because I usually think of down as being negative, right? And that's why I don't like H, because we're not H usually says to me height, and height is measured from the bottom up, but we're measuring the depth from the top down, okay, because the pressure increases with depth. So what I'm going to do, I'm going to reorient this just so that I don't have that problem of a downward direction being an increasing value. So what I'm going to do, I'm going to draw my dam sideways, okay? So I'm going to draw a coordinate plane here. All right, so I have X and I have Y. And instead of drawing my dam in the normal orientation, I'm going to draw it sideways. And I'm also going to put the water level at on the y-axis, okay? Because I want X is going to be my depth of the water, okay? So if I put the water level on the y-axis, then X will measure the depth of the water in the positive direction, which is the way I want it to go. All right, so we have this dam is 20 meters high, but the water is 4 meters from the top of the dam. Okay, so I'm going to draw the top of the dam over here. Okay, and then I'm going to kind of center it on the x-axis. And then it's a trapezoid shape, right? So I'm going to kind of draw it sort of symmetrically. As symmetric as I can get, right? Like this. Okay, so here's the bottom of the dam. Okay. The water level is at the y-axis. Okay. And then this point here, okay, so the dam is 50 meters across the top. So this essentially represents the top here. The top is this, and here's the bottom. Okay, so this is the bottom. All right, so if the distance across the top of the dam is 50 meters, so if I've centered this on the x-axis, then this point here is 25 meters up. Okay, and if the water line is at 0, then the x-coordinate here is a -4. Okay, so this is the point -4, 25. Okay, so this one will be -4, -25. Okay, so then the whole top is 50 meters. All right, and then this point here, so if the dam is 20 meters high, but the water is 4 meters from the top, then this point here is going to be an x value of 16. And then the distance across the bottom of the dam is 30 meters, so this is going to be 15 meters up. Okay, and then this point down here would be, if I wanted this point, this is going to be minus. It's going to be, whoops, not minus. It's going to be 16, minus 15. Minus 15. All right, so clean that up here so it's I can read it. So this is 16, minus 15. Okay. Now, the only reason I'm doing that really is to get some sort of equation for the boundary of this because I have this sloped side, right? And if I do that, then basically I've got a line between 2 points, and I can find, if I've got 2 points, I can find the equation of a line, right? So I'm going to use the point slope form of a line. So I'm going to take y minus the y value of one of the points, and I'll just use this 16, 15. So the y value here is 15, and then that's equal to the slope. Okay, so got to look at rise of a run. So it looks like I'm going down by, I'm going down by 10 and over by 20, right? 10, 20, right? So my slope is a minus 1/2, and then I want to do x minus the x value of the point that I've chosen, which is 16. All right, so let's clean that up a little bit. This gives me y is equal to minus 1/2 x. So half of 16, well, minus 1/2 times minus 16 is a positive 8, and then I'm going to add 15 to both sides, so I get 23. Oops, 23. All right, 23. All right, so now I have an equation, and I've got the depth. The depth is increasing in the x direction, so x is the depth, because I've sort of reoriented this, my dam shape. Okay, so what do I want to do? I want to, I'm actually going to erase this thing that I drew to give you the, whoops. Just drew that to give you the slope, but because now I want to look at a strip that's at a constant depth. So I'm just going to look at a strip here. Okay, it's going to be a really thin strip so that the strip is roughly at a constant depth, right? So we have a strip that's delta x wide, right? And the distance here is essentially y, where you go up and down in the y direction, right? So essentially y is given by my line here, y equals negative 1/2 plus 23, but I really need twice that, because it's, that this distance y up to the line that that represents the side is just half the distance of the strip. So, all right, so let's write this out. So we want the area of one strip, and that's going to be twice the y distance, which is minus 1/2 x plus 23, right? And then the width of the strip is delta x. All right. So now if we take the area of that strip times the pressure at that depth, we get the force on one strip. So the force on one strip of the dam is equal to 9,800 x, right? So 9,800 times the depth, right, times the area of the strip. Now, if I multiply through by 2, I'm just going to go ahead and do that to make this simpler. I'm going to get minus x plus 46, and then delta x. Okay, so this 9,800x is essentially my 9,800 h that I had up here. I'm just using x instead of h as my depth. All right, so now we have the force on any given strip. So now I want to integrate this over the depth of the water. And the depth of the water is just going from 0, which is the water line is at 0, to the bottom of the dam, which is at 16 feet down from the water line. Okay, so, and we're going to integrate 9,800, and I'm going to multiply through by the x. So I'm going to get minus x squared plus 46x dx. All right, well, now it's just pretty much just arithmetic now and a little calculus. All right, so we get 9,800, and then when I integrate my polynomial here, I get minus 1/3 x cubed, and then plus 1/2 times 46, which is 23x squared. evaluated from 0 to 16. All right, so now it's just a matter of putting it in my calculator. Now this is a big number because I got 16 cubed and 16 squared. So if I write this all out, I get 44 million 322,133.33 newtons. Now, your calculator will probably tell you it's something more like 4.43 times 10 to the 7th newtons in scientific notation. So that's probably the better way to write that number. But, so that's a lot of force, right? That's a lot of force on that dam. So that pretty much takes care of all the examples in this section, and I will see you in class.